Welcome back, class. So what we want to talk about today is being able to look at a reaction and predict if it's going to be an SN1, E1, or an SN2, E2 type of mechanism. And there's going to be these guiding principles that when you look at them, and you look at them in a holistic way, look at all of those principles, you will be able to identify what mechanism you should invoke. And then once you've decided on the mechanism, then you can use that mechanism to predict the product and what it should look like. So the factors that we're going to look at are, we can enumerate these right here. We could say the strength of the attacking species. And then we'll take a look at the concentration, and I'll just go like that, the brackets for concentration of the attacking species, and I'll abbreviate that with ATT. The third thing that we want to take a look at is the leaving group ability and how that affects the mechanisms. And the type of carbon that the type of the carbon the leaving group is attached to. So another way of saying that, we could just say hybridization states. What is the hybridization state of the carbon that the leaving group is attached to? And that's really important. So another thing is solvent effects. So with solvent effects, that's going to affect the strength of the attacking species. So kind of like 1 and 5 are kind of connected. And then we have another principle that we have to watch out for, and that would be heat. And we represent heat in reactions with that delta symbol. Okay, so those are the principles that we want to discuss. And so we are going to jump right into that and take a look at the first one, the strength of the attacking species. And why is that so important? Now, just to make sure we're all on the same page, these principles are going to tell us when we see a reaction what mechanism is going to occur. So for the first factor here, the strength of the attacking species, here is a bullet point that you want to write down. So stronger the nucleophile, which is the attacking species. So attacking species are what? They could be nucleophiles or they can be bases. So when I'm talking about an SN2 reaction, okay, stronger the nucleophile, so we can make that pull. Stronger the nucleophile, that's going to mean that's going to promote a faster SN2 reaction. Barely got that on the screen. Stronger the nucleophile, faster the reaction. Okay? So that's a key point to remember. So let's see here. I want to see if there's something on the PowerPoint that I want to talk about here. So taking a look at that PowerPoint here, I'm looking on my screen. I can't see it right on the screen that you see it. I have to look at a different screen. So that's why I'm looking away. So here is a list on that PowerPoint of strong nucleophiles and weak nucleophiles. And what you're seeing there are typically strong nucleophiles are what? Negatively charged. And then the weak nucleophiles are generally neutral. And so we're going to focus our attention on the strong nucleophiles at the moment and how they favor or promote a SN2 reaction to make them go faster. But before we look at that, when we take a look at two nucleophiles, how do we know which one is stronger? So if we come back to the PowerPoint slide, let's take a look at that RO minus, versus, let's say, the carboxylate, which would be the RCO2 minus. Do you see that on the PowerPoint slide? So we want to compare those two, but now we have to be careful. The R group, I'm going to translate it now into something else. The RO minus, let's say that is going to be methoxide. And I'm cutting that off, so I'm going to turn off the PowerPoint now. So methoxide versus, let's just keep it generic here, like that, okay? So that to that. When we look at these two, which one is going to be the stronger nucleophile? Well, we just use the same principles that we've learned when we're looking at the strength of acids and how we use the cardinal rule to look at the stability of the conjugate base. So when we use the cardinal rule here, we can see, let's write out the cardinal rule. So there's the cardinal rule, and we go through it, and we compare these two. They both have the same charge. They both have the charge on the same atom. So we go to the next one. We see that this molecule doesn't have resonance. This molecule does have resonance. Hence, this guy is going to be the more stable base. That's how it's kind of drawn. Or let's just keep the, that's going to be the more stable nucleophile. More stable. Okay? That's the more stable nucleophile. So what does that mean from an energetics perspective? Well, if we draw it right here, just energetically right here, because the carboxylate is more stable, it's going to be right down here. And so just by process of elimination, that would make the methoxide up here, like so. So now that we've established which one's higher in energy, we can then also say, hey, this guy's higher in energy, shown right there. So it's going to be the most unstable, which would then say, hey, that's the most reactive. That guy's the most reactive because it's higher in energy. Remember, when molecules are high in energy and are uncomfortable, they want to get more comfortable. And the way that they do that is by reacting with something. Because when you react, you can get lower in energy and more stable. So this guy is the more reactive species, which then, because it's more reactive, because it's the most unstable, it is going to be the stronger nucleophile. So that's our stronger nucleophile. So when we take a SN2 reaction and we say which of these two nucleophiles is going to make the SN2 reaction run faster or proceed faster, we would say the stronger nucleophile. And we've identified from this whole process that that is our stronger nucleophile. So this one will have a faster SN2 reaction than that nucleophile. Okay. So let's clear off this board. Now let's take a look at a SN1 reaction and how the nucleophilic strength affects the rate. So if we take a look at our PowerPoint again, let's take a look at some of those weak nucleophiles, because weak nucleophiles favor SN1 mechanisms. So if we take a look and compare the reaction rate of an alcohol versus, let's say, an amine. Okay, so we see 3, there we go. There's ammonia. So we have a generic alcohol and ammonia. And when we look at the PowerPoint slide, which one's the stronger nucleophile? Well, the amine is going to be the stronger nucleophile, okay? When we take a look at a reaction here, let's do a molecule that looks like this. That's somewhat correct. Okay. Put a chlorine here, actually. We need a good leaving group. Now, if we compare the ROH versus the amine, which one is going to go faster? Okay. Now, if you're thinking SN2, we've learned that stronger the nucleophile, the SN2 reaction will go faster with the stronger nucleophile. But with SN1, the rates of these two is the same. Same rate. The strength of the nucleophile does not influence SN1 reactions. And why is that the case? Because when you look at the rate law, or the rate for an SN1 reaction, remember this, so if our rate is going to equal, and this is for our SN1, that's going to equal just the, what is so dependent, for an SN1 reaction, what species is responsible for the rate? It's the alkyl halide. Compare that to the rate of a SN2. That is dependent upon the alkyl halide and the attacking species, which I'm just going to represent like that. Or since it's SN2, we can actually put in there the nucleophile. So do you see the difference in the rates? So in an SN2, the rate is dependent on the nucleophile. And so if you have a stronger nucleophile, the reaction is going to go faster. But in a SN1 reaction, there's no attacking species over here. It doesn't influence the rate at all. It's just the concentration of the alkyl halide. And so the strength of the nucleophile for a SN1 doesn't influence it. So what we can say in conclusion for this concept of attacking species strength is that if you have a strong nucleophile, that's going to favor SN2. And if you have a weak nucleophile, that's going to favor SN1. Now, the same principles that I've taught you here for SN1 and SN2 also apply for E2 and E1. So if you have a strong base, that's going to favor E2. And if you have a strong base, or not strong, a weak base, that's going to favor E1. So same principles here, okay? Because when you look at the rate of an E2, it is dependent upon the alkyl halide and the base. But if you look at the rate of an E1, that is only dependent upon the concentration of the alkyl halide. Okay, so it's basically the same concept here. Okay. But what we have to be very careful of is just because you have a strong nucleophile does not mean that nucleophile can be a strong base. Let me show you that via the PowerPoint. So if we take a look here at the PowerPoint, this is showing you the strength of nucleophiles, right? But in this next slide, right here, at the very top, you will see that it is the strength of the base. So this slide with the strength of the nucleophiles is now on the bottom of this slide, okay? Now I want you to make some comparisons here. On the far right of that slide, you see the R minus. It is a strong nucleophile and it is a strong base. You see that comparison when you're looking at the slide? But now take a look at iodine, the I minus. Do you see how it is a red and a strong nucleophile, but a blue, weak base? You see that? So the iodine is, or iodide, because it's an anion, the iodide is a very strong nucleophile, but a weak base. And so we have to be careful about that, because when we talk about electron-rich attacking species, you could fall into the trap of thinking that, oh, it's electron-rich, so it is automatically a strong nucleophile and strong base. Not necessarily, okay? Now, if we take a look at the iodide, for example, and just reason through it, why is it a strong nucleophile? Well, because it has negative charge and it is very polarizable, which means that the electrons in the electron cloud can move around. And polarizability is a key feature for a nucleophilic attack. But why would iodide be a weak base? Well, think about it. What happens if we treat this as a base? It's going to want to abstract a proton from an acid, right? And so that would just mechanistically come in, abstract that proton like so, and generate what? That would generate hydroiodic acid. That's an acid. What's its pKa? Around -10 or 11? So we know if it, with iodide, when it behaves as a base, it's going to generate an acid, which then, it's an acid. Acids want to donate their protons. So iodide is a weak base because it generates a very, very strong acid. So it's just not going to do it. All right? And you guys didn't see any of that because of the PowerPoint slide. So let me rehash that. There we go. So let's start over. So why is iodide a weak base? Because when it abstracts a proton from an acid, it generates hydroiodic acid. So you guys saw all that part over there, but you missed this part. Okay. So in summary, why is, when you take a look at our iodide, our bromide, and our chloride, why are they weak bases? Because they generate strong acids if they act as a base. But why are they strong nucleophiles? Because of their negative charge and their polarizability. All right. Another thing that you have to be aware of is when you look at that period or that PowerPoint slide, do you see that the OR minus is a strong base and a strong nucleophile? All right. So there's some exceptions to that. Erase all this. All right. So when we look at that PowerPoint slide, we see RO minus And according to that PowerPoint, that is a strong base and nucleophile. That's what we see on the PowerPoint slide, right? But this R group right there is going to influence if it's both of these. So for example, this OR minus could represent ethoxide, like that, right? And according to our chart, I look up on PowerPoint and it says RO minus is a strong base and a strong nucleophile. And for this particular molecule, that is true. So we'll just go strong base, strong nucleophile, like that. But if we added some steric bulk to that R group, so compare it to something that looks like this, like that, tert butoxide, and if we were using our PowerPoint as our guide, we can get a little misinformation here, because this does in fact represent an RO minus. But this one is only a strong base. And the reason why that is only a strong base is because of this steric bulk right here. That steric bulk is going to prevent the tert butoxide from being a strong nucleophile. So you're going to encounter strong, bulky bases, meaning they're strong because they have a negative charge, but because they're bulky, they can only act as a base. They cannot act as a nucleophile. All right, so that right there is the first factor, the strength of the attacking species. All right, so that principle right there, there's a lot to it. The second factor that I want to take a look at is the concentration. Right, and this one's pretty straightforward. So recall when we were looking at the rates, okay? And let's look at the rate of an SN2. What's the rate dependent upon? The concentration of the alkyl halide and the concentration of the attacking species. And in this case, it's going to be a nucleophile. But when you compare that to the rate of a SN1, that's only dependent upon the concentration of the alkyl halide. So what we see here, that when we increase, let's say we double the concentration of the nucleophile, it's going to double the rate. But if we double the concentration of the nucleophile in an SN1 mechanism, it doesn't affect the rate at all. So what we can say here is when we look at a reaction, a concentrated attacking species is going to favor SN2. So if our concentration of our nucleophile is concentrated, that's going to favor SN2. But if our nucleophile concentration is low or dilute, it's going to favor SN1. And so the same principles apply when that attacking species is a base. So if our base being really strong, if it has high concentration, that's going to favor a E2 mechanism. And if our base, right here, a weak base, is low in concentration, that's going to favor a E1 mechanism. And it comes back down to these rate laws right here. Okay? So when you see a reaction, let's do something like this. And we have a, let's do hydroxide like this, okay? What's our product going to be? Well, it depends on the mechanism. But that's not what I want to talk about. What I want to talk about is when you see a reaction, you're always going to assume that the attacking species concentration is high, that the concentration of that attacking species is concentrated. That's the assumption you go by every single time. The only way that you're going to know the concentration of that attacking species, if it's dilute or not, is if I put and spell it out. If I go like in parentheses and go dilute. Now you know that because this attacking species is dilute, the mechanism may, because it's dilute, favor a SN1 or an E1. Okay. Now I use the word may be a SN1 and an E1 is because we cannot look at just one of these principles and make a decision on the mechanism. I cannot look at this reaction and say, oh, it has a dilute attacking species, so it's either SN1 or E1. No, I can't make that judgment call because I'm ignoring all the other principles that I had listed on the board. So we have to look at all of the principles and come to a conclusion. But this right here, that dilute, is one bit of information that suggests that the reaction should be SN1 or E1 because it's dilute. All right? So that one's a pretty straightforward principle. All right? The next one, or factor 3, is the leaving group ability. Okay. So let's clean up this board here. So factor 3 is the leaving group ability. So we take a look at these two alkyl halides. Okay. And we're comparing those. Which one is the better leaving group? Because alkyl halide, so we know those are leaving groups. Okay. And so what's that going to generate here? That's going to generate a secondary carbocation plus our chloride. Same for this guy down here. Secondary carbocation plus our bromide right there. Which one is the better leaving group? In this particular case, we could just use a size argument, like the chloride is smaller than the bromide. And we've learned that larger the volume that the atom has for the negative charge to move around in is going to be lower in energy and more stable. So we can say from this analysis that the bromine right here is the better leaving group because after it has left, it's going to be more stable than the chloride. And so if these two atoms could talk, the bromide's like, yeah, I can leave. Doesn't bother me at all. Whereas the chloride's like, I can leave, but it's going to hurt a little bit. And I'm going to be uncomfortable in this way. Okay, so leaving group, you have to, in order to do these 4 mechanisms, you have to have a leaving group. Now, for the SN2, E2, SN1, and E1, every single one of those mechanisms needs a good leaving group. But now I want to take a look at which, with respect to leaving groups, which mechanism does it affect the most? So the leaving group ability of this bromine right here, would it affect the rate of an SN2 reaction more or an SN1 mechanism? So if we take a look at the mechanism in a SN2 fashion, right? What's the step? In an SN2, it comes in, breaks off, in a concerted fashion, right? Very simple, straightforward SN2. Okay, that. But in a SN1, what's the first step in the mechanism? Leaving group leaves, generate a carbocation, then we'll use water in this case. The attacking species will then come in and attack and generate O like this. And then we would have to do a proton transfer with some more of that water to generate our alcohol, like so. So looking at these mechanisms here, this one is an SN2, this is an SN1. We're having the same alkyl halide, same leaving group, but this halide, or this bromine right here, the leaving group ability is going to affect the SN1 reactions more than the SN2, because what's the first step in the SN1 mechanism? The leaving group has to leave first. In an SN2, the leaving group does in fact leave, but it's kind of leaving because the oxygen atom here is kind of like kicking it off. And so what we can say here is that better the leaving group, okay, where do we want to write this? The better the leaving group is going to influence and affect SN1 and E1 mechanisms far greater than the leaving group ability will affect SN2 and E2 reactions. So it is true that all four mechanisms need a good leaving group. It's just a better leaving group is going to favor our SN1 and E1s more so, okay? It affects it more. Now, if we take a look at an alcohol, take a look at an alcohol. Can we say to that alcohol, hey, I want you to leave and generate a species that looks like this? Can that happen? I hope you're all saying no. Alcohols are horrible, horrible leaving groups. But what if you do really, really need to get rid of that alcohol? What if you do need to get it to say, hey, I need to leave? Well, you can convert alcohols into good leaving groups by treating it with a strong acid like hydrobromic acid. Look at what happens here. We have some lone pairs on that alcohol. Make sure, okay. That can come in, grab that proton, break it like so. And then we're going to have what? Attach the water there. And now that oxygen atom is positively charged. And we still have our bromide floating around. And now look at what can happen. That molecule right there looks like water. It is water that's attached to this carbon. So water is a good leaving group. So we could have the bromide come in an SN2 fashion, attack, kicking off the leaving group to give us our product. And I know this board's getting messy, so our product is going to be down here. Br plus water just left, like that. So we can, in fact, convert bad leaving groups into good leaving groups if we need to. Also, I want to highlight what kind of molecule did we make? We made a alkyl halide. So put that in your notes where you keep track of reactions and what products you form. And so you could phrase the question in your notebook, how do I make alkyl halides? And you would then answer your own question by saying, you take an alcohol and treat it with a strong acid, and you get your alkyl halide. All right. Okay, so that is factor 3, leaving group ability. And if you can remember, the leaving groups affect SN1 and E1 better. All right. So let's take a look at factor 4, which is basically the hybridization states. Hybridization states of the carbon that the leaving group is attached to. So I'm going to start drawing a molecule, and I want you guys to take a moment and figure out how many good leaving groups are in this molecule. All right. So let's see here. Yeah, we'll do it like that. How many good leaving groups are in this molecule? All right. Pause for a second and answer that question honestly. Now, if you said, hey, there's 2 leaving groups, then we're missing something. Okay? Because in previous lecture videos, I said the leaving group, which we see 2 halogens here, so you are thinking that they're 2 good leaving groups, but there's another layer of understanding. Those good leaving groups have to be attached to a sp3 hybridized carbon. And so we see the hybridization state of that carbon is sp2, and that one is sp3. So this is not a good leaving group because it's attached to sp2. So in that particular molecule, there's only 1 good leaving group. Okay. So let's draw another molecule. Let's take a look at something that looks like this. And let's treat it with some water in an SN1 fashion here. How many of those leaving groups would work for this reaction? How many of these groups here would react with the water? Well, we first have to establish what we just learned over here. Is every single carbon that the leaving groups are attached to, are they sp3? Yes, they are. They're all sp3 hybridized carbons. So we have 1, 2, 3 good leaving groups. But when we invoke a SN1 mechanism, there's only going to be 2 plausible choices. And we have to remember that if we choose to attack here or use this as a leaving group in an SN1 fashion, what's the first thing that happens in an SN1 mechanism? The leaving group has to leave. And if that leaving group leaves, what are we going to generate? We will generate, let's draw it. Erase this for a second. We would generate a primary carbocation. We do not generate primary carbocations. It's too unstable. Does not work. But can we generate a secondary carbocation or a tertiary carbocation? Yes, we can. So what we have to be careful of when we are looking at a molecule like this, not only do we have to identify that the alkyl halide is attached to sp3 hybridized carbons, but we have to identify that, hey, this alkyl halide right here is a primary, that one is a secondary, and that one is a tertiary alkyl halide. And so that primary alkyl halide, if it undergoes an SN1, it would become a primary carbocation. That's no go. That would become a secondary carbocation and a tertiary. And those are okay because those carbocations are stable enough that they can form those intermediates. So what we can say for a SN1, we have primary alkyl halides, secondary, and tertiary. Which ones are not an option? Cannot do that one. All right. What about a SN2 mechanism? So in an SN2 mechanism, we have to use a strong nucleophile, which looks like that. We invoke SN2. How many of these alkyl halides would react with the hydroxide in an SN2 fashion? Hopefully you're seeing, based off of what we've talked about previously, that the tertiary is off the table. Can't do it. And why is that? Because of the mechanism. The hydroxide here comes in backside attack. And if it tried to do backside attack here on that tertiary alkyl halide, the sterics here would prevent that from happening. So you cannot have a SN2 mechanism on a tertiary alkyl halide due to sterics. But can that mechanism work for a secondary and a primary? Yes, it can. Now, let's take a look at the same molecule here. It's getting a little bit messy, so let's clean it up. What if we use the hydroxide right there as well? And let's invoke an E2. What if we have a E2 mechanism? We have primary, secondary, and tertiary. Okay. Can it react with all three of these alkyl halides? How do E2s work? Yes, it can. Okay. So the E2 mechanism is a little bit more promiscuous, that it can react with both of them. Okay. However, if you invoke a strong bulky base like terbutoxide right there, those are going to favor primary and secondary over this tertiary alkyl halide due to a steric argument. All right. So this E2 right here, you have to really look at the base to see what kind of base it is, if it's a small, strong base or a strong, bulky base. But if we just looked at this particular scenario, a strong, small base without steric bulk, it will do all three. Okay. Let's see here. We got one more, yes. Let's do E1. So that would have to be a weak base. So E1, we would have primary, secondary, and tertiary. Cut off the tertiary. Let's take it down here. So E1, primary, secondary, and tertiary. Which ones of these do all three alkyl halides work for an E1? No, it doesn't. Because what's the first step in a E1 mechanism? The leaving group has to leave. And so it follows the same trend as the SN1. Primary is off the table. Secondary and tertiary are. Those can work. And it all comes back to the mechanism. The leaving group leaves first, generating a carbocation, so we have to assess the stability of those carbocations. Okay? Now, primary carbocations don't form. That's what I've been saying. But there's something that, there's some kind, I don't want to call it really an exception. It's just another layer of understanding. But students at first glance would be like, hey, that doesn't work, when in fact it does. And so I want to show you two examples that are very common here. And that is when you have a benzene ring, okay, and you have a good leaving group or a halogen. Can this, so what is the hybridization state of that carbon? That is sp3. So the halogen can in fact leave. And when you look at this carbon there as well, is that a primary, secondary, or tertiary alkyl halide? And it is in fact a primary alkyl halide. Okay? But look at this. It does in fact leave. It can generate that. And it does kind of look like a primary carbocation, but it's not. And that's because it's attached to this benzene ring. Look at what this benzene ring can do. It can have a resonance structure that helps to stabilize what looks like a primary carbocation. Well, we call this species, we don't call it a primary carbocation, we call it a benzyl cation. Or a benzylic cation. Benzyl, benzylic, interchangeable in this particular case. Okay? Another example that you need to be aware of is something that looks like this. Can that bromine just leave? Yes, it can. But first we identify that, hey, that is still sp3 when we look at it. And then that looks like it's primary. And so we're thinking that it can't happen. The leaving group can't leave, but it does, because what do we generate? We generate something that looks like that. And so what is that guy called? See, this is an allylic. And allylic cations can in fact form. So why is that so stable? Why can that form? You guys can already see what's going to happen. We have resonance. So that carbocation is resonance stabilized. And so we have a benzylic cation and an allylic cation that at first glance, they look like they're primary, but they're not. They have a different name and they are stable due to resonance. So what we can take a look at is the relative stabilities of some typical cations. And I just want to make a list for you so you can see their stabilities. So we have a cation that looks like this. Okay, that's called a Weinlich cation, and that's very unstable. And then we have our methyl cation. That's a little bit more stable. And then we have, let's see here, our primary carbocation. that is representing a secondary carbocation. Okay. And those secondary carbocations right there are approximately kind of just as stable as our allylic. Okay. And also approximately like the benzylic. And I'm going to cut that off, darn it. I'll draw it right here, like that. Yeah, you can see that. That's good. All right. And then you barely see that less than sign right there. But then we can have our tertiary carbocations, are typically the most stable. Okay? So this is kind of just a general way of looking at the stabilities of carbocations and how you would rank them. Now, as we progress in the course, we can see a little, over in this area, a little switching occurring depending on the situation. And we'll see those when we talk about them. But for right now, this is a good way of looking at the stabilities of these cations. Okay, let's take a look at factor 5, which is solvent effects. So I'm just going to go straight to the answer, and then we'll talk about the reason why that is the answer, okay? So we have two types of solvents that we need to be aware of in organic chemistry. And the first one is polar aprotic solvents. And those are going to favor SN2 and E2 mechanisms, all right? And then you have something called polar protic solvents, and those are going to favor SN1 and E1 mechanisms. Okay. Now, why is this the case? Okay, so that's the answer. But why? Well, let's go to the PowerPoint because that's going to show us some things right here. So these slides, it looks like I skipped this slide right here, so I want to highlight this one real quick. And this one is all about the leaving group ability. So you've been taught that halogens are good leaving groups. That is true. But you also have other types of leaving groups shown on the slide called sulfonate anions, and those are good leaving groups. And we have a variety of them. We have a mesylate, a tosylate, and a triflate. And you can see how they look. So if I wanted to draw a mesylate leaving group, it would look like this. O attached to a sulfur, double bonded O, like that. Okay? So that would be a mesylate. Now, mesylates and all these sulfonates right here behave the same way. If you want the bromine to leave, it leaves. If you want the mesylate to leave, it leaves. Same thing. It just looks a little bit different. And then when you look at the tosylate would look like this. Six-membered ring and a methyl group, right? So there's our tosylate. It would behave the same exact way. But when we draw our tosylates, drawing this big piece out every single time can be a little pain in the butt. So instead of drawing it all out, we could just go like this, OTS. And if we wanted to abbreviate our mesylate, it would just simply be O-mesylate. And you did see that. So let me redraw it like that. And how would you do the triffolate? You would just go OTF, okay? So those are just new leaving groups that you need to be aware of, and they play a significant role in organic chemistry, okay? So this slide right here is just showing you good leaving groups, okay? Okay, now back to factor 5, which is solvent effects here, okay? There's two, we already talked about the two types of solvents, but I want you to pay close attention to the protic solvent on the left, okay? Do you notice how close the solvent is around that anion? Now, let's back up for a second and evaluate the difference between a protic solvent and a aprotic solvent, okay? That's really important to understand. So a protic solvent or a polar protic solvent, let's do it that way. Polar protic solvents, okay, are solvents much like alcohols, so ethanol or water. When we take a look at these molecules, we know from general chemistry that both of these molecules are polar. Okay, so that checks that word right there. They're polar molecules and they're solvents. Now the protic right here is referring to protons. Now the proton of interest has to be one that can hydrogen bond. How do we know if a hydrogen bond can form? Is if the hydrogen is attached to a fluorine, oxygen, or nitrogen atom. So this hydrogen right there can hydrogen bond. And because we have a molecule that has a hydrogen that's attached to an oxygen, fluorine, or nitrogen, that can hydrogen bond, and so that makes it a protic solvent. So the protic is referring to a proton that can hydrogen bond. When you compare polar aprotic, for example, acetone, which is also shown on the slide there on the right, that's acetone, looks like this. We can see that that molecule is in fact polar, but aprotic means that it does not have a hydrogen on the molecule that can hydrogen bond. Yes, it does have those 3 hydrogens on those carbons. Yes, it has hydrogens, but it does not have hydrogens that can hydrogen bond. That's what we're looking for. So hydrogen bonding capability, protic, hydrogens that cannot participate in hydrogen bonding, aprotic. So this is a polar aprotic solvent. These are polar protic solvents. And because of this difference in the ability to hydrogen bond, affects how they interact with anions. And we can see back to our PowerPoint slide there that the molecule on the left with water as the polar protic solvent can get really, really close to that anion, and it can hydrogen bond. Okay? Well, let me take that back. You can see that those partially positive hydrogens on the water, and why are they partially positive? Because of the electronegativity and the polar molecule. So we have a water molecule. If we draw it right here, like this, do you see how we have a, because it's polarized, we have one side of the molecule that is partially negative, negative, and the other side is partially positive. So do you see how the partially positive side of the water molecules interacting with that anion? And that interaction is really, really strong. But in contrast, do you see that the acetone or the polar aprotic solvent in the molecule on the right, do you see how its proximity, or do you see how the solvent molecules, which are the acetone molecules, how close they are to the anion? They're not as close as the water molecules are. And one reason that that's the case is because of the sterics of those methyl groups. It doesn't allow those, the partial positive of the acetone. So when we look at acetone, there's a partial positive and a partial negative part. And because of these methyl groups right here, okay, those methyl groups kind of prevent this partial positive piece of the molecule to interact very strongly with the anion. So just look at the distance. When you look at that PowerPoint slide, look at the blue partial positive on the group on the left. Do you see how close those partial positives are to the anion? And compare that to the structure on the right. You see those partial positives are further away. So there's a less of an interaction between the solvent and the anion for the polar aprotic solvent. And so this has an effect on the ability of those anions to react. So let's ask a question here and kind of tie this all together. Okay? So I'm going to leave that PowerPoint slide up. Which is the stronger attacking species? Bromide versus chloride. Do you remember at the beginning of this video, we talked about how this right here is more stable. So that makes the chloride more reactive because it's less stable. So it's the stronger attacking species. Do you remember that analysis? And what principles did we invoke to come to that conclusion? It was a size argument, right? Okay. But now the strength of these attacking species is also going to be dependent upon the solvent. Okay? Because what we're seeing on the PowerPoint slide is that a polar protic solvent is going to solvate an anion very, very well. You see that there's more water molecules around the anion, and they're closer to the anion. So it stabilizes or it solvates the anion more. And when an anion is solvated more heavily, it becomes more stable. More stable means lower in energy. And when it's lower in energy, it becomes less reactive. Whereas a polar aprotic solvent, the one that's shown on the right, the image on the right in the PowerPoint, does not interact with the anions as well. And for our purposes, we're going to just make the assumption or statement that polar aprotic solvents don't solvate anions very well. Okay? So that's something that you write down. That's really important to remember. Polar aprotic solvents do not solvate anions very well, whereas polar protic solvents do in fact stabilize anions very well. So if we take a look and ask the question, which is the stronger attacking species? Well, it's all dependent on the solvent, okay? So if we take these two species and put them in a solvent called DMF, which stands for dimethylformamide, and that is a polar aprotic solvent. Right? And polar aprotic solvents do not solvate anions very well. So when we take a look at these two, we're going to just make the assumption that there's no solvent present. Okay? And thinking that there's no solvent present, when in fact there really is, but we're just ignoring it because polar aprotic solvents don't solvate anions very well. So they don't offer any stability to the anion. So all we're going to do now is look at these two and assess which one's the most stable. And we're just going to use what principles we've learned up to this point. And in this particular case, remember when we can, let's get rid of this, carbon, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Remember that we have electronegativity arguments and a size argument. When we're going down a column like this, we're going to look at size as a factor and not electronegativity to explain stability. So because we're going down, the bromide is larger. We're ignoring the aprotic solvent because it doesn't solvate the anions very well. We can say, based off of size, that this is going to be the more stable anion. So that makes that unstable in comparison to this, which would make the chloride the stronger attacking species. All right? That would be the stronger attacking species in a polar aprotic solvent. Now, let's change it up. What's going to happen to the strength of these attacking species when we change the solvent to polar aprotic? So let's put in ethanol. What's going to be the stronger attacking species? Now let's think about the principles here. That's polar aprotic. So those do solvate anions very, very well. And we have two anions right here. So they're going to be solvated very well. Now it comes down to which anion is going to be solvated better. And the size here does influence that once again. The smaller anion is going to have more localized charge due to its size. Because it's smaller, the negative charge is more localized. And when that happens, the solvent is going to interact more strongly with a smaller anion. So this anion is going to be solvated more than the larger anion. So what is that going to do to the energy between these two? If this is more solvated, it's going to lower its energy more so than the bromide. And so that's going to make the bromide the least stable in this situation. And so the bromide is going to be the least reactive of the two. So it's going to be the stronger attacking species. Do you see how the solvent has flipped those? So in aprotic, this guy's going to be the stronger attacking species. Oh, no, wait. Let's pause for a second. Let's not mess this up. So polar aprotic, this is going to be solvated more, so that makes this the stronger attacking species. Okay? But in a polar aprotic solvent, we're going to pretend that there's no solvent around because aprotic solvents don't solvate anions very well. And so when you compare the stability of these two, that one's going to be more stable because its size. So that would make that guy the stronger attacking species in a polar aprotic solvent. Okay? All has to do with how the solvent interacts with the anion. Okay? So let's draw some tables here and some charts and kind of just summarize all of this. All right? So let's take a look at nucleophilic strength. Nucleophilic strength as we go down. Just like that, okay? And I want to take a look at the nucleophilic strength when we're looking at polar protic solvents, okay? So what we're showing here is that in polar protic solvents, the iodine is going to be the stronger nucleophile than the fluoride. So what we're doing is energetically, we have 1, 2, 3, 4. What we're going to see right here is that the iodide is at the very top and the fluoride right there is at the very bottom. Okay? The fluoride is going to be lower in energy, more stable. Why? Because we're in polar protic solvents. The smaller atom is going to be solvated more strongly, and that stabilizes it. And so the larger atom is solvated less, making it higher in energy, hence more reactive. So nucleophilic strength, as you go down a column in polar protic solvents, the larger atom is going to be the stronger attacking species or the stronger nucleophile. Okay? Now, what if we go across? Okay? What if we go, let's do a different colored marker here. I'll draw another energy diagram right here. We'll have 4 energy levels, like so. What if we're going to go across the periodic table? What is going to be the stronger nucleophile? Okay. Now this is an interesting thing, is that it goes in this direction for nucleophilic strength. So that's saying that the carbon, which is going to be a carbon anion, is going to be higher in energy than the fluoride. Okay. Now notice that this is still in polar protic solvents. Okay. So why do we have a trend in this direction? Why is the carbon anion a stronger nucleophile than the fluoride anion? And the principle is that when you go across the same period here, the sizes of the atoms don't change that much. So the actual volume of the carbon anion versus the fluoride anion, about the same size. So the solvent is going to solvate these anions basically to the same degree. So that's a wash. How the solvent interacts with these anions doesn't matter anymore when trying to determine which one is the stronger nucleophile. So we have to go to another principle. And now we're just going to look at the stabilities of these two species. And we can't use a size argument because they're the same size. So what can we do? We can look at electronegativities. And we know the fluoride or the fluorine atom is more electronegative than the carbon. And so the carbon can tolerate a negative charge better. So it's going to be lower in energy, less reactive, so making the carbon the stronger nucleophile. All right? You see that? Now let's take and change up the solvents now. Let's change the solvents to polar aprotic. Polar aprotic solvents, what's going to happen now? Do the trends change? And they do in fact change. All right. So when we are looking down a group in a polar aprotic solvent, which species is going to be the stronger nucleophile? Well, it's going to be the fluoride. Okay, it's a complete switch. All right. So that would mean that we have to switch these. Our fluoride is now there, and our iodide is right there. Now, why is there a switch now? Well, because we are in polar aprotic solvents. Aprotic solvents don't solvate anions. So we ignore that there's a solvent present for determining which one's the stronger nucleophile and just go based off of what we've been taught in the past. Do we use electronegativity arguments when we go down a group? No, we use size. And we can see that based off of size, a negative charge on a larger iodide is going to be more stable, lower in energy than a negative charge on a smaller fluoride. And so because fluoride is higher in energy, the least stable, going down this group, that's going to make that the most reactive, and it's going to make it the stronger nucleophile in this series. Now, does this arrow change? Does the nucleophilicity change there? And that arrow does not change because, once again, solvents are not going to solvate anions very well because that's how polar aprotic solvents work. And we have the size argument here in which the chloride or the carbon anion and the fluorine anion are the relative same volume. So we just have to go off of the principles that we've learned before. We can't use a size argument in determining if the carbon is more stable or the fluoride, okay, because they're the same size. But what can we use to invoke the stability? We can say electronegativity. The fluoride is more electronegative, so it can stabilize the negative charge better. So it's going to be lower in energy, making the carbon anion the stronger nucleophile. All right. So I think I've already written this down somewhere, but I'll just do it again just to cover our bases here. So when we have polar aprotic solvents, that's going to favor what? SN2 and E2. Polar protic solvents is going to favor SN1 and E1. Now, another principle that I want to share with you to help put this all together is the fact that when you have a attacking species or a anion, okay, depending on the okay, let's put it this way. This anion is going to have solvent around it, okay? And in order for that anion to act as a nucleophile, it has to basically shed this solvent. It's not going to be able to shed all of it, but it needs to be able to get rid of some of it, of that solvent, in order for that negative charge to come in and attack the electrophile. We've got to get rid of that solvent. So if you have a attacking species, so if we compare a bromide versus this bromide, and I'm going to represent solvent with this green marker, so I'm going to invoke a lot of solvent on that bromide and just a little solvent around that one. So you see they're still both bromide, but this bromide right here is going to react faster and better, and it's going to be a stronger nucleophile because it has less solvent around it. Whereas this right here is going to be a weaker nucleophile in this particular solvent system because it has more solvent. And in a SN2 and an E2 mechanism, what's happening? It is coming and attacking in a concerted fashion, okay? So we want this attacking species to be, the word is naked. It doesn't want solvent around it because more solvent around it is going to limit its ability to do the SN2 attack, okay? So that's another reason why polar aprotic solvents are going to favor SN2 because there's going to be less solvent around the attacking species, which allows it to attack better. And we've already learned that the strength of the attacking species influences if it's going to be an SN2 or an SN1 type mechanism. Stronger attacking species promote SN2 and E2. On the flip side, why do polar protic solvents favor SN1? Well, that has to come back to this idea of leaving group. So if we have this compared to this, but in this one we have polar protic solvent, and this one we have polar aprotic solvent. And the solvents, we're just worried about the anion. So when this anion leaves like this, and this anion or bromine leaves like that, what difference does it look like? Well, this is polar protic, so that means it's going to have a lot of solvent, and this one's going to have less. So that guy leaves, that guy leaves, but which one's going to want to leave more earnestly? Now, in this case, they're both the same leaving group. But you can see that, hey, in polar protic solvents, the bromine's going to want to leave. It will leave easier than in polar aprotic solvents because in polar protic solvents, when it leaves, it becomes an anion. And when it's solvated by the solvent, that makes that bromide lower in energy. This bromide isn't solvated very well because of the polar aprotic solvent, so that makes this guy higher in energy than that guy. And so when you compare these two scenarios, which one wants to leave better? This one, because it gets solvated more strongly and it's more stable. Isn't that cool? Okay. Now, the next factor that we need to talk about is heat and what that does. Okay, so let's take a look at a reaction here. Now I see we have a secondary alkyl halide, and I want to treat that with a sodium hydroxide, so a strong attacking species here. Now we could go in two ways here. We could go in this path that's going to give us this product right here. All right, like that. And what type of mechanism is that right there? So let's be a little bit more particular. Let's put that as a wedge right there. And so that's going to make that a dash, okay? Hopefully you can see that is a SN2 mechanism. And so we have a substitution. So SN2 for substitution. But we can also have a E2 mechanism right here in which we could generate the alkene plus the chloride plus what? The hydroxide abstracted a proton, turning it into water. Okay? Now, when we take this species here, treat it with the hydroxide, we're going to have competition here. And that's what this whole lecture is about, is trying to figure out what is it going to do. But when you tack into this principle here of adding heat, I have said it's going to favor the elimination product. Okay? So why is it going to favor the elimination product? Well, it comes back to Gibbs free energy. When you take a look at the equation here, like that, okay? So when we apply heat, well, let's bag heat for a moment. Let's take a step back. When you look at the substitution versus the elimination, which one has higher entropy? It goes from 2 species to 2 species versus 2 to 3. So this molecule, or the elimination product, has more entropy. And when we look at this equation right here, when we increase entropy, that's going to be a favorable process, right? But now when you tack in heat, what are you doing? You are multiplying the temperature by the entropy. And in an elimination, we have more entropy, and now you're going to multiply it. And so that's going to make this term right here that much more negative, which is going to give us a more negative delta G, which is a more favorable reaction. So heat favors elimination because of this term right there. Okay, so you have to understand here that when we're going to go through all these principles, we use heat as a tiebreaker. And I'm going to show you what I mean by that when we go through a problem. Okay, so just remember, heat is used as a tiebreaker. Okay, and we represent heat with the delta symbol. Okay, so if we did this reaction right here, in this particular case, we could see basically a mixture of products. We could have our alkene and an alcohol. Okay, but if I changed and added some heat to it, then clearly it's going to be our alkene. So so we'll leave it at that. Okay. So now I want to show you how you're going to use all of these principles in order to decide what a reaction is going to do, if it's going to be any of the 4 mechanisms. Okay. I'm just going to double check my notes to make sure I haven't missed anything. Okay, so we will do this via PowerPoint. All right, so let's turn on our PowerPoint again. And it always starts me at the beginning, so we have to go through it here. Okay, so here's our reaction. We have the chloropentane, and we're going to react that with sodium bromide. Okay, and I'm going to show you step by step how I can look at that particular reaction and figure out what mechanism I'm going to invoke. And once I've decided on a mechanism, I will do that mechanism, and that will show me what products I've obtained and which one's going to be the major. So the first thing that you have to do when you see a reaction, it's written right there, determine whether the substrate has a suitable leaving group. And when we look at that molecule, we see that there is a chlorine attached. And so chlorines are good leaving groups. Okay? We also have to make sure that the leaving group that we've identified in step 1 is attached to a sp3 hybridized carbon. That is critical, sp3. Okay? So that's step 2. Now that PowerPoint slide is just reminding you of the different types of alkyl halides here. Okay? So when I look at the alkyl halide, right there, it is what? A secondary alkyl halide. When you have a secondary alkyl halide, all four reaction mechanisms are on the table. A secondary alkyl halide can undergo SN1, SN2, E1, and E2. Okay? But you can see on that chart as well, what if our molecule was only a primary alkyl halide? Then our only two options are going to be a SN2 and an E2. If it's a primary alkyl halide, our job is easier because we went from 4 possible mechanisms all the way down to 2 just looking at step 2. But I've chosen a harder problem to illustrate this. When it's a secondary alkyl halide, all 4 mechanisms are on the table at this point in time. So that's step 2, making sure what type of alkyl halide you have. All right. Now, step 3, I go through the principles that I've discussed. The strength of the attacking species, the concentration, the leaving group ability, and the effects that solvent has on the reaction. Okay? Okay, let's see, right here. Okay. So what do we have here? So adding up the 4 factors. So we want to take a look at the strength of the attacking species. Notice how it's sodium bromide. That is the attacking species. Sodium bromide is an ionic compound, so it is going to dissociate. So what we actually have is the bromide, which is the Br minus, right? So we're going to have our Br minus right there as our attacking species. Now, when we take a look at that, is bromide a strong nucleophile? I look at my little chart there and it says, hey, Br minus is shown in red, and that's going to be a strong nucleophile. I'm keeping a mental note there. But when I look and ask, hey, is bromate a strong base? It shows that it is a weak base. Okay? So what that does for us is when you have a difference between weak and strong, always go with the strong. And the strong, what type of strong is it? Is it a strong base or a strong nucleophile? Well, in this particular case, it is a strong nucleophile or a weak base. So we go with the strong. So it is a strong nucleophile, okay? And so what does that tell us? We're going to create a check mark here. So it's a strong base, it is a strong nucleophile, so that favors SN2. But is it a strong base? No, it's not. So I'm not checking the E2. But is it a weak base? Yes, it is. And weak bases favor E1. So you see on that table there, I'm looking at factor of strength. And the bromide right here is telling me that it could do a SN2 and an E1 based off of what it is. Strong nucleophile means SN2. Weak base means E1. And I put those check marks. Okay? And I'm going to keep a tally mark of all these check marks. And at the end of this analysis, the column that has the most check marks is going to be the mechanism that we choose. So we go to the next idea here, concentration. Okay? You can see that the sodium bromide doesn't have parentheses that says, hey, it's dilute. So we know it's concentrated. So what does a concentrated species favor? SN2. It also favors E2, But because of the previous factor, the strength, it told us that E2 wasn't an option. So we're not going to put for concentration E2. We're just going to leave it as just SN2. All right? So the concentration is high, which favors SN2. Now we go to the next, the leaving group ability right here. Okay? So does it, the chloride there, is it a decent leaving group? And yes, it is. And so leaving group's ability really affects all 4 reaction mechanisms. Okay? So that one's an easy one. If it has a good leaving group, all 4 choices are a possibility. Okay? So we have all the check marks there when we're just looking at the leaving group only. Okay? Now, the other factor there is the solvent. What type of solvent do we have? Well, we have DMSO. Okay? DMSO is a polar aprotic solvent. So when you look at the solvent, you have to figure out if it is polar protic or polar aprotic. I told you that DMSO is polar aprotic. Okay? So if I know that it's polar aprotic, what mechanisms does that favor? So a polar aprotic solvent favors SN2 and E2, and you can see that I have 2 check marks there. And now I just sum up each column, and you can see SN1 only has 1 check mark, SN2 has 4, E1 and E2 both have 2. So we have a clear winner. The mechanism is going to be SN2. And so now that we identified what mechanism that we have, we now need to do it. Draw it out. And so there's the mechanism shown there on the PowerPoint where it's looking at the SN2 mechanism. So we're going to do backside attack. It's going to invert the stereo center and give us our one product. Okay? Now, the factor when we consider heat, okay, that is only used to break a tie. Okay? So let's say, for example, if our particular problem had SN2 with 3 check marks and E2 with 3 check marks, how do we break the tie? Well, if heat was added, then it would favor the elimination. If no heat was added, then we would favor the SN2. That's how we're going to handle that. Okay? So like the slide says, we temporarily ignore the heat component to it unless there's a tie, and then we go back and look at the reaction to see if there's any indication that heat was added. When I look at that reaction scheme, I don't see a delta symbol. I don't see the word heat anywhere. So I'm just going to assume that no heat was added. But that only comes into play when we have to break the tie. So class, what we're going to do is continue working on problems like this when we come to class. So I hope this has been helpful. And if you need any additional help or have any questions, please reach out. I'm more than happy to help.